Welcome to lab number 5. This lab will help us get ready for checkoff number 1 next week of the major project. We're going to develop some very important equations that will help us to calculate all of the R's and C values for the major project. We'll get started by calculating 2 out of the 11 R's and C's. We will write 4 example equations representing the 4 major principles that are employed in the major project. And then we'll finish off by filling in a table of 5 approximations needed for the major project. Now, to see how all this fits in, I would suggest you reread in the textbook, at the very end of the textbook, the major project up to page 223 to see how this all fits together. So let's get started with the lab today. First, let's turn to the top of worksheet 2 and see table 2, or when it's in the textbook, C2, which is going to be our choice of clinical units to be used in the solution for all of the variables in the major project. And these clinical units that we're going to choose now will be used by everybody in the class. Otherwise, the TAs would go crazy trying to compare numbers. Well, for pressure, we have 2 possibilities. We have Pascal in SI units or millimeters of mercury, which are clinical units. Since we're doing a clinical simulation, it makes sense for everybody to use millimeters of mercury as the units for pressure. Please mark that down in the table. For volume, we have a couple of choices, both clinical, milliliters or liters. Well, based upon our past experience, it turns out that liters give us numbers that are a little bit more manageable. So let's choose liters as our units for volume, not milliliters. Now for volumetric flow rate, that's volume per time. We've already said that volume will be liters. The time could be milliseconds, seconds, or even minutes, because cardiac output is given in liters per minute. Well, liters per minute are more uniform, more average. We want something that represents more the instantaneous flow rate, and so we're going to choose liters per second. That means that seconds will be the units for time, not milliseconds, in our major project. Now, as background for our simulation of the systemic cardiovascular system, here is a simplified, compact anatomical view of the cardiovascular system. It's composed of 2 parts. The systemic cardiovascular system is driven by the left ventricle, and it circulates oxygenated blood through all of the organs of the body to be returned back to the right side of the heart, and that pumps blood from the right ventricle through the lungs to pick up oxygen. The right side of the heart is a lot lower in pressure, about 1/3 of the pressure of the left side of the heart. They're both in series with each other. Well, in a little bit more detail on the systemic cardiovascular system, the left ventricle drives blood through the aorta into the arteries, arterioles, and then through the many, many billions of capillaries that we have, where it's collected by the venules, the veins, and the vena cava, to be returned to the right side of the heart. Well, for our major project, to simplify it, we're going to assume that the return blood goes directly through the left atrium into the left ventricle, bypassing the pulmonary circulation in the lungs. That makes the model a lot simpler. Now let's see how this schematic, which is our key schematic for solving the major project, relates to the anatomy. Off here to the left is the left ventricle, the heart, and then followed by the aorta, large and small arteries and arterioles, which are lumped together, and then the capillaries, and then the venules, veins, and vena cava, again lumped together. The reason that we've lumped some of these together is to reduce the total number of equations and Windkessel elements that we have to solve for. Notice that we have 5 remaining. 2, 3, 4, 5 Windkessel elements remaining. If we went any further, it would reduce the model down to something that would be too simple to be accurate. This is called, therefore, a lumped element model. Let's follow the course of blood. It comes out of the left ventricle through the aortic valve and then through each of these vessels in series, in order, before returning back through the mitral valve to the left ventricle. Something about the nomenclature of the subscripts. We'll use a subscript H for the left ventricle, which is the heart in our case, an O for aorta, because we're using an A for arteries, and a C for capillaries, and a V for veins. That means that the pressure, let's say, at the top of the aorta, the middle of the aorta, is P sub O. The compliance of the aorta is C sub O, and the volume of the aorta is V sub O. Something about the flow of blood now. The flow of blood through each of these vessels has an odd subscript, because that represents flow going around the circuit. The flow that goes in and out of each of the vessels has an even subscript. The flow goes in during systole to expand the volume of that vessel, and then comes back in the opposite direction during diastole, and the vessel contracts. That's especially important for the left ventricle Q10, where Q10 during diastole represents the filling of the heart during diastole, and then when the heart squeezes to eject the blood, Q10 reverses flow and comes back out through the aortic valve. Notice that all of these have even subscripts. Now let's turn to worksheet number 1. And this is the worksheet where we're going to develop some equations that will help us to find all of the R's and the C's in the major project. Starting first with the R's. We're going to use Poiseuille's law, or to be a little bit more exact, the simplified version of Poiseuille's law, to find the R's. You remember that Poiseuille's law in simplified version said that if we had a blood vessel with a resistance R and an inlet pressure P1 and an outlet pressure P2, that the flow rate of blood through that vessel Q was given by Q equals P1 minus P2, inlet pressure minus outlet pressure, divided by the resistance. Or in a slightly different form, if we call P1 minus P2 the pressure drop delta P, then Q becomes delta P over R. Now that equation is good for any instant of time, and we'll use it quite a bit to find the changing flow rate Q in the major project during the 800 milliseconds of a cardiac cycle. But if it holds at any instant of time, it will also hold on average. So let's take that equation, turn it around and solve for R, and let the pressure differences be average pressure differences, and the flow rates be an average flow rate. And that is the equation that we'll use to find the values of R's. Why average? Well, we're going to assume, and this is a pretty good approximation, that all of the R's in our major project are constants. They don't change during the few cardiac cycles that we're going to model. So if the R's are constant, it makes sense to use average values for pressure and flow rate Q. Well, for 3 of the R's, namely for R sub OA, which is between the aorta and the arteries, and R sub AC, which is between the arteries and the capillaries, and R sub CV, between the capillaries and the veins, for those 3 resistances, I'm going to say that the denominator, Q sub average, is just the cardiac output of the heart on average. Why? And why did I pick those 3 to single out those 3? If you look back at the schematic, you'll note that those 3 resistances, the segments have no valve in series with those vessels, and therefore the flow rate through those vessels does not start and stop during systole and diastole. And notice that the cardiac output is actually the flow around the loop, so it makes sense that the average flow through each of those is the cardiac output. Where do we find the cardiac output? The cardiac output can be found in a table in the textbook, table C3 here. And notice that down at the bottom right is the cardiac output for a healthy human in liters per minute, between 5 and 6 liters per minute. You choose any number within that range. It turns out that towards the top of that range gives a little bit better answers, but you choose whatever you'd like in that range. And notice it's liters per minute, so you're going to have to change that value to liters per second because of the units that we are going to use for volumetric flow. So that gives cardiac output. Now each of you is going to enter in these equations into your worksheet, and you might also want to make a note of where each of these values comes from. I won't do that here, but you could, on your worksheet, you could make a note that cardiac output comes from table 3, table C3. Now, how about the average pressure in the numerator? Well, let's just use 1 to start with for the resistances. And I'm going to say that the average pressure drop between the aorta and the arteries on average is given by the average pressure in the aorta minus the average pressure in the arteries. That makes sense. Where do we find those values? Well, there is a graph in the textbook that's very helpful. We call it the pressure drop graph, and it shows the pressure drop in the vertical axis in units of millimeters of mercury as we go around the systemic loop, starting first with the left ventricle, the heart on the far left here, and then through the aorta, arteries, capillaries, and veins. Now, to find the pressure on the average, notice that when we're in the first part of the systemic system, the pressure changes between systole, where it's high, and diastole, where it's low. And so we need the average pressure. I'm going to draw a line here, that the average pressure follows probably this dotted line right here. So I'm going to draw that in. I know that you can't draw that in because you don't have paper copies of this, but you can imagine where that line is. And we'll call that the average pressure line. Notice I've made it closer to diastole than to systole. The reason for that is that your heart, your system, spends more time in diastole, more than twice as much time in diastole as it does in systole. So the average should be closer to the diastolic line than the systolic line. Now let's find T sub O on average, in the aorta on average. Down here you'll notice that the aorta actually has 3 segments to it. The ascending aorta, the thoracic aorta in the chest, and the abdominal aorta down in the stomach region. Let's pick somewhere in between those, right? Maybe right there. And at that point, we'll put a ruler and go straight up to where that ruler crosses the average line, which is this point right here. And I'm going to say that that is the pressure in the aorta on average. You can go off to the left there and just estimate what the pressure is on the scale on the left for the pressure in the aorta on average. How about in the arteries? Well, remember we've lumped the large and small arteries along with the arterioles all together. So where are we going to say the arteries lie? Well, I'm going to say maybe somewhere in the center between the large and the arterioles, maybe right about there. So if we put our ruler at that spot to find the pressure on average in the artery region, and we go up, I'm going to say that the pressure in the arteries on average is that dot right there. And you can look off to the left and estimate what the pressure is on average in the arteries. Put those two values in a calculation later for finding the pressure drop across from the aorta to the arteries. Let's go back now to the other resistances. Well, for R sub AC and R sub CV, it follows the same sort of pattern, just change the subscripts. So we won't do that, but you can do that when you calculate these later. So just etc. there. And that gives us 3 out of the 5 resistances. The other resistances are unique in that they have a valve in that sequence, in that segment. For example, R sub HO is the resistance of the aortic valve. And notice that the aortic valve only lets flow go through that resistance during systole, when the aortic valve is open. So the flow is not constant there, and it's harder to find the average over a complete cardiac cycle. So let's find just the average when that valve is open, because that's the only time the aortic valve has a pressure drop across it in the forward direction. So for R sub AO, I'm going to say that the average flow, which is Q1 in this case, through the aortic valve, on average, is just occurring during systole. And so the pressure drop, the total volume out, is the stroke volume divided by the time in systole. Now the stroke volume is how much comes out of the heart just during systole. And the time of systole is just the length of time that the aortic valve is open. Where do we find these values? Well, the stroke volume is found in the very same table that we used to find cardiac output, right here. Stroke volume is 70 milliliters. Change that to liters, and that's for a healthy heart. Put that in the numerator, and then for the denominator, we have to find how long systole lasts. Well, we find that from a very, very helpful diagram in the textbook called the Wiggers diagram. And the Wiggers diagram actually is a time-based diagram. Along the horizontal is time. The 800 milliseconds is a typical cardiac cycle for a heart that's at rest. That's the one we're going to use. Everybody's going to use 800 milliseconds here, or 0.8 of a second. And up in the vertical are various pressures in the heart and the aorta and volumes. Notice that the ventricular time is defined as the time from when the mitral valve first closes, and then the aortic valve follows quite quickly after that, to where the aortic valve closes. That's our definition of the systolic time. So the time from there to there is how long systole lasts. So we'll call that T sub systole. And that goes into the denominator of Q1 on average. While we're at it here, notice that diastole starts at the end of systole, starts right there when the aortic valve closes. And then in this Wiggers diagram, it sort of wraps around and comes back again to finish up with this segment right there. You add those two segments together to get the time of diastole that we'll need in a few minutes. I ought to point out why, sort of unusual, why the Wiggers diagram starts just before systole, not right at systole. Well, the reason that there's a delay in the start of the Wiggers diagram is that allows us to look very carefully at what happens during the isovolumetric contraction during systole from there to there. If all of that was shoved off to the left axis, it would be harder to see. So that's why the Wiggers diagram has the timing that it does. Well, now that we've found T sub systole, which is 350 minus 100 milliseconds, put that into seconds, and that becomes the denominator there. Make a mark that you found stroke volume from the table and T sub systole, the time of systole, from the Wiggers diagram. Next, we need to find the numerator. So we need to find the pressure drop on average across the aortic valve, because that's what R sub HO represents, on average. And that is just the pressure in the heart during systole minus the pressure in the aorta during systole, because that's the pressure drop across the aortic valve. Where do we find those values? We can find those again on the Wigger's diagram. We bring that back here, and we'll take, let's say somewhere in systole, why don't we take maybe an average medium point in systole, which would be right about somewhere in here, and we take our ruler and we go up to the very top of the Wigger's diagram, because at the top of the Wigger's diagram are the curves for both the pressure in the heart, which is the very upper curve. It's the largest pressure in the heart in the whole system during systole. And here's the aortic pressure on this line right here, which is lower than the heart. And the difference between those two is what opens up the aortic valve, to cause the aortic valve to open. So the pressure in the heart during systole, I'm going to say, is where the ruler touches that very upmost curve right there, whereas the pressure in the aorta is where the ruler touches the lower curve right there. Now those two dots aren't very far apart from each other. You can actually go over to the scale on the left and sort of estimate the pressure difference between those two. It's not very much, and actually in a healthy person you don't want it to be very much. And the reason for that is any pressure drop across the aortic valve is lost to propel the blood around the rest of the system. So you don't want a big pressure drop across the aortic valve. Incidentally, if you have a disease such as aortic valve stenosis, where the valves of the aortic valve may be closed off and don't open up as much, then the resistance of R sub HO becomes much greater, and there's a much greater pressure drop between the heart and the aorta during systole. Those are the two dots that you'll use to estimate the pressure drop between the heart and the aorta during systole to find R sub HO. Oh, there's another place we can find the pressure drop across the aortic valve, and it's completely consistent with what we've just seen. If we go back to this pressure curve, we'll notice that up here at the top, we see that the aortic valve pressure drop is between the heart right there and between the aorta right there, and it gives us about the same pressure drop that we just found from the Wigger's diagram. Use either one to get the pressure drop. And that allows us then, those two values, to find the resistance R sub HO. How about the last of the 5 resistances, R sub VH? That one represents the mitral valve, R sub VH, the pressure drop between the veins and the heart, R sub VH. Q9 flows through it. So I'm going to say that Q9 on average is again just the stroke volume divided by the time of diastole, which we just found a second ago. Why stroke volume? Because whatever goes out comes back in. And so that will allow us, you can find those values like we found them for R sub HO. And you put those in to find Q9 on average, that's the denominator. For the numerator, we need delta P between the mitral valve, and actually that includes the atria, on average. And as you might expect, that's the pressure in the vein on average, minus the pressure in the heart during diastole, not systole, but diastole. Where do we find those values? Well, the pressure on average in the vein can be found once again from this curve in the textbook, figure C4, because if we go over here, we've lumped the venules, the veins, and the vena cava and the right atrium together. Somewhere in the middle of that is where I'm going to say the veins can be represented on average, maybe right here. So we go up from that spot with a ruler and find where the ruler crosses that line, and off to the left we can estimate what the pressure is on average in the veins. Oh, notice something, that when we get to the capillaries in the veins, the pressure doesn't jump between systole and diastole anymore. There's not much pressure pulse because the pressure pulse from the heart has been damped out by the compliances and resistances of all the previous vessels before it gets to the capillaries and the veins. So in the capillaries and the veins, the pressure is pretty constant during a cardiac cycle. And you'll see this when you solve for them in the major project. Well, that gives us the pressure in the veins right here. That comes from figure C4, the pressure curve. Let's find the pressure in the heart during diastole. To find that, we go back to the Wiggers diagram right here. And I'm going to say that diastole, which lasts pretty much from here and wraps around to there, about the middle of diastole is where I'm going to try to find the average. And the middle of diastole is right, yeah, you can pick your own point, but I'm going to say it's maybe somewhere right about in here. And I put my ruler there and go up and find the pressure in the heart during diastole. Believe it or not, the pressure in the heart is now the lowest of all the pressures during diastole, because that's what allows the mitral valve to open up to fill the heart, and it has to be very compliant with low pressure in order to fill easily. So the pressure in the heart during diastole is the lowest line here, and the ruler crosses that line right about there. Let's let that point be the pressure in the heart during diastole. You go off to the left and estimate what the pressure is and put that in when you do the calculations, when you get around to doing the calculations for the pressure in the heart during diastole. And that will allow you now to find the numerator and the denominator to find R sub VH. Now let's turn to the bottom of the first worksheet. In this area right here, we're going to enter into equations that will allow us to find all 6 of the compliances that are needed for the major project. The equation that we will use is one we've seen before, and that's the compliance equation. That if we have a compliant blood vessel whose symbol looks something like that, that has a compliance C and a volume V, the pressure inside that vessel, P, is given by the following expression. It's the total volume inside the vessel minus the residual volume of the vessel, which I will follow the textbook and temporarily call that V sub 0, divided by the compliance C. Now that equation holds instantaneously, and we're going to use it in the major project to follow the changes in the pressure each millisecond of the 800 milliseconds that makes up a cardiac cycle. But if it holds instantaneously, it'll also hold on average. And we'll use the average form of that equation, solving for C, to find the various C's in the system. And on average, C is equal to the average volume minus the residual volume, which is always constant, divided by the average pressure in each of those vessels. And that's the equation we will use to find the 6 C's. Now for the 4 compliances that are constant, and that is an approximation, it's a pretty good approximation, for the 4 compliances that we're going to assume constant during a cardiac cycle, the aortic compliance, the arterial compliance, the capillary compliance, and the venous compliance, for each of those 4, we need to find, for the numerator, the average volume and the residual volume in each of those vessels. Where do we find that? Well, we go back to a table from the textbook, table C3 that we've seen before, and up near the top are the total volumes in each of the compartments of the systemic cardiovascular system along with their residual volumes. Now notice the aorta is all by itself. These are milliliters, so change them to liters. But for the arteries and arterioles, they're listed in the table separately. We've lumped those together, so make sure you add those 2 values together. Don't average them, and add these 2 together in liters to be the residual volume. Capillaries are all by themselves. The veins, venules, and vena cava, we have to add each of those 3 together to find the total volume in that compartment and the total residual volume in that section of the cardiovascular system. I'm just going to make a note of that here. that we need to add the lumped elements together from that table. Make a note on your worksheet of where these values came from, namely table C3. Now for the average pressure in the denominator, that's going to be easy because we found the average pressure in each of those vessels when we found the resistances above on this sheet. Just use those same pressures. Now for the next two compliances, that may cause you some wonder because if you look at the schematic, we only have 5 Windkessel elements here. 5 Windkessel elements. So we only have 5 compliances. Where do the 6 values come from? Well, it turns out that C sub h, we always call it just C sub h, has 2 limits. It goes between 2 limits. It changes. It is the one compliance of all of them that varies during a cardiac cycle. That's what the arrow through it, that means. And it goes between a lower limit during systole when it squeezes hard to force the blood out through the aortic valve and the rest of the system. And then it goes during diastole to a very high value where it becomes very compliant and soft to allow it to fill easily during the diastolic period. So C sub h goes between 2 limits, and the limits are what we're going to find next. So to find the limit for systole, which we call C sub hs, and once again that is the limit of C sub h during systole, we'll use that equation up above, but we'll put in systolic times for it. So C sub h S is equal to the volume in the heart during systole minus the residual volume of the heart divided by the pressure in the heart during systole. I can get rid of one of those values because it turns out, believe it or not, that the residual volume of the heart acts in modeling as though it is 0. Residual volume of the heart is 0. I'll show you later some human studies done at Johns Hopkins University that shows that operationally it looks like the residual volume of the heart is 0. Now to find the volume of the heart during systole, we go to our friend the Wigger's diagram. And the Wigger's diagram we've used before, and we've said that on the average, sometime about in the middle of the time of systole is where we're going to find our values. So there's the value in the middle of systole we found before. We will take our ruler and go up to the middle of this diagram, because in the middle are the graphs of the volume in the heart, the volume in the left ventricle, which is the heart, and where the ruler crosses that line is a dot. I'm going to say that that is the volume of the heart during systole. Go off to the left and estimate what the volume is in milliliters, change that to liters. And that will give the numerator. For the denominator, the pressure in the heart during systole, well, actually we found that before. So at the same middle part of the systolic time, we'll put our ruler there and we'll go up to the very top of this graph, and that upper dot is what we found before. The upper dot is the pressure in the heart during systole. Go off to the left, estimate that, and use that for the denominator. That will allow you to find C sub hs. For C sub hd, which again is the upper limit of C sub h, we'll put in diastolic times. C sub hd, therefore, is the volume of the heart during diastole minus the residual volume of the heart divided by the pressure in the heart during diastole. Well, immediately we can get rid of the residual volume of the heart. We've said that we're going to let that be equal to 0. The volume in the heart during diastole is once again given by the Wigger's diagram. Bring that back up. And we said that on average somewhere in the middle portion of the diastolic time, which is about that point, that's where we can find the average values. We put our ruler there and go up and find out where the volume of the heart crosses that ruler. It's that point right there. Go off to the left and estimate what the volume of the heart is during, on average, during diastole. That's the numerator. For the denominator, we want the pressure in the heart during diastole. Well, again, this is actually found in the Wigger's diagram. At a middle point of the timing of diastole, right about where that is, I put our ruler there, we go up, and actually the very lowest curve during diastole is the pressure in the heart. The pressure in the heart is the lowest of all of the pressures during diastole. That's what opens up the mitral valve when the pressure in the heart is lower than the atrial pressure. That opens up the mitral valve to allow the heart to fill. And so the pressure in the heart during diastole is where the ruler crosses that very lowest line, that point right about there. Go off to the left axis, estimate what the pressure is, and put that in to the denominator for C sub HD. And I think now we've found equations that will allow us to find all 5 R's and all 6 C's. We need to do that for next week when we check off next week. Now, returning to worksheet number 2, in the center of that worksheet are regions where we're actually going to start practicing to calculate the resistance values and the compliance values. We'll start with just one resistance, R sub OA, just to see if the equations work for us. Use the equation from worksheet number 1 and calculate the value for R sub OA there. Put the answer here with the appropriate units. And the same way for C sub V. Calculate C sub V here and put the answer here with units. That gives us practice for what we're going to need next week, where we have to calculate all 5 R's and all 6 C's. Now, if you wanted to get a head start on next week's checkoff, which is checkoff number 1 of the major project, you could calculate all the rest of the R's and all the rest of the C's. But do that on a separate sheet of paper that you have, and do not turn it in with the worksheets for this week's lab. Rather, save it and turn it in next week. Now, down at the bottom of worksheet number 2 is where we're going to write some typical equations for each of the 4 key principles that were included in the major project. Pressure from compliance is the first one. So we'd like you to handwrite in here the equation which gives the pressure in the arteries as a function of each of the milliseconds, that's the index I, as we go through a 800 millisecond cardiac cycle. Write that equation right in here. It will use the volume in the arteries at that particular time point, I, the residual volume in the arteries, and the compliance in the arteries. Put that equation right here. Note a couple of things. First is that the subscript A can't be made a subscript in MATLAB, so it's up at the same line, at the same level as the P. So the subscripts are not really subscripts when we put them into MATLAB, but that's okay. We can figure that out. Notice something else, that V sub A is not vectorized because it is constant. It's the residual volume, which is constant. In the same way with C sub A, that is not vectorized. There's no I behind those. But all of the parameters, all of the variables that change in time are vectorized with an I in the parentheses behind that variable. Oh, and then finally, I use I as an index indicator. I stands for index. Rob McLeod does not like that because MATLAB also lets I be equal to the square root of -1, the imaginary number, unless we override it here. So you can use I use I, just don't tell Rob about that. Going on, let's use Poiseuille's law, the simple Poiseuille's law, to find out an equation for Q3. This will use 2 pressures. You have to put in the subscripts here, and 1 resistance. Note that if we had one of the flows that was in line with a valve, we'd need a couple of more lines. Q1 and Q9 are in line with a valve, so they're going to add some if statements. And that's going to add a couple extra lines in this section of Poiseuille's law. Going on to the conservation of volume, write an equation for Q4 Here, it's also vectorized using two Q's. I'll let you figure out what the subscripts are for those. And then write an equation for Euler's update of volume V sub A at the updated time, the next time I plus 1, based upon one volume, one flow rate Q, and the increment of time dt. I'll let you put the subscripts on that. Now notice that what we're doing here is very similar to one of your homework problems that you'll be doing this week for homework. Let me show you what that homework problem looks like. It is problem number 2 on set number 5, and it is very similar to an example in the textbook, 6.1. And this actually has just one segment of a vessel. You break it up into two Windkessel elements, one on the left and one on the right. And you will use all of the same equations that we've just written down for this homework problem. It follows along example 6.1 in the textbook, but there is a different configuration here. Just be aware of that. The valve has been flipped over to the right side of the vessel rather than the left side of the vessel. And the pressure P3 is given to you. Pressure P1 by this graph, and pressure P1 is a constant. That's a little different than the major project where the pressures vary from time to time. I call this homework problem a mini major project. Make sure you understand it when you do it for this week's homework, because it's a very important predecessor to the major project. Now let's turn to the last of the worksheets, which is Table 4, or 4C in the appendix, which lists some of the approximations that will be necessary for us to carry out our simulation of the systemic cardiovascular system. It turns out every modeling requires some approximations. Otherwise, the simulation would be too complex to carry out. And I've actually counted about 15 approximations that we need for our modeling. For this table, you need to fill in 5 approximations in this column right here, based upon what you have learned about the various equations and modeling that we're doing here. Now, I've started you out with an example. The pulmonary circulation is not modeled in our model, and that includes the right heart, the right atrium, and the right ventricle. Now, for every approximation, there's a price to pay. There'll be something that can't be modeled anymore. And for this approximation, it's pulmonary edema, which is pooling of the blood in the lungs, which often accompanies left heart failure, can't be modeled. Now, I've made a judgment that its effect on the final accuracy is medium here. And for each of your approximations, in addition to listing one thing that's lost in the model because of that approximation, I'd like you to make a judgment about whether you think the effect on the final accuracy is minor, medium, or major. I don't think any of them are going to be major, because that means you couldn't trust the final result much at all. But I'll let you make a judgment about what you think the effect is of each of your approximations. You will not be graded on this particular center column here, but just make a judgment. Now, a couple of warnings about these approximations. First of all, you can't double count. And what we mean by that is if you say for one approximation that we've lumped together the arteries and arterioles, for the next approximation you can't say that we've lumped together the veins, venules, and vena cava, because that's the same concept, and that would be double counting. And then also, if you list one of the 4 approximations necessary for Poiseuille's law to be valid, you can only list one, not more than one of that. Incidentally, if you get your worksheets by filling in a blank sheet of paper, please use a ruler to make this table in landscape orientation, and you don't need to write out this example. So I'll let you finish out this table to complete this week's lab. And then one last item. When you turn in your worksheets, please keep track of worksheet number 1 and save it, because we're going to need it extensively in next week's lab. Well, I hope you've found this week's lab to be beneficial in preparing you for next week's lab, which is checkoff number 1 of the major project. There are a lot of aspects to next week's lab. You need to complete calculating all of the R and C values, and you have to start writing out the main program for the major project. So be sure you get started early on next week's lab. See you then.